Assalamu alaikum dear students. So far we are done with a couple of tests for the convergence and divergence of the series, namely integral test, comparison tests, which includes direct comparison and limit comparison test. One thing is common in all the tests, that the series under consideration had only positive or non-negative terms. So none of the tests actually address the convergence or divergence of the series consisting of negative terms. So, but in general, we may encounter with the series having negative terms as well. So, how to check the convergence and divergence of such series? So, in this section, we are going to address this problem, and we are going to introduce a few tests uh, like absolute convergence test, root test, and ratio test. And all these tests revolve around the series having positive and non-negative both types of the terms. So let's start. When some of the terms of the series are positive and other are negative, the series may or may not converge. Of course, like any other infinite series may or may not converge. So for example, we have this series and it has negative and positive terms, alternate negative and positive terms. So this is actually a geometric series with common ratio minus 1 over 4, and we can observe that absolute value of this common ratio is 1 over 4, which is less than 1. So according to the rule of the convergence of geometric series, this series is convergent. Now there is another geometric series given in 2, and you can see that common ratio for this is 5 over 16 with negative sign, negative 5 over 4. So in this case, absolute value of the ratio is 5 over 4, which is greater than 1. So, according to the convergence and divergence of geometric series, we can conclude that this series is divergent series, right? So, there is some cancellation. You can see that in the term series 1, there is some cancellation in partial sums, so which may be assisting the convergence property of the series. However, if we make all the terms positive in the series 1, right, to form a new series, that is series of absolute values, like this, 5 plus 5 by 4, and this becomes a series of absolute values. So actual series, if we have actual series sigma an, then its corresponding series of absolute value can be written like this. So we see that it still converges, right? Now what we did, we just take the absolute value of each term. So the series 1 becomes, let me show you series 1 again. This is the 5 minus 1, 5 by 4. So initial first term is 5, and we had minus 1 over 4 as common ratio. So actual series will be like this. And this is the series by making every term positive. That is the series of absolute values. Now this series is still convergent. So we see that it's still convergent. So for a general series with both positive and negative terms, we can apply tests for convergence studied before to the series of absolute values of its terms. So in doing so, we are led naturally to the following concept, that is absolute convergence. So let's see what is this. A series sigma an converges absolutely or absolutely convergent if the corresponding series of absolute values converges, right? If this series converges, then the series of absolute values converges. We say that the given series converges absolutely. So the geometric series 1 is absolutely convergent. We observe too that it is also convergent. The series itself is also convergent. So this situation is always true, right? If the corresponding absolute series is convergent, then the original series also converge. An absolutely convergent series is convergent as well. So this is the point we are going to uh, make in this section, which is very important. So an absolutely convergent series is convergent as well. So to keep it in mind, this fact must be noted carefully. So which we now prove. So we are going to prove this fact now. And this leads us to the absolute convergence test. And this is theorem number 12 in the book. So this theorem states that if sigma absolute an, that is the series of absolute values, converges, then sigma an converges. Alright. So in order to prove that, we know that this an lies between negative absolute value of an and the positive value, absolute value of an, and you know this result from the calculus 1 you studied in last semester. So what we are going to do, we are just going to add absolute value an to whole series. Okay, so we are going to add absolute value of an here, here, that is we have this, and similarly we are adding this. So absolute value of an adding to the inequality, we have this result. This left hand side becomes 0 and the middle term becomes an plus absolute value of n, and the right term becomes 2 times absolute value of an. Okay, now what is given? Given is this series is convergent. Okay, so now we can use the direct comparison test. This series is convergent, we know that, and this is greater than this series. So since this series is convergent, by direct comparison test, smaller series also converge. So what we can conclude that sigma an plus absolute value of an also converge because this series converge. Alright, now we can use this in order to conclude the convergence of this series. Now, an can be written as an plus absolute value of an minus absolute value of an. We just added and subtracted the absolute value of an. So it doesn't make any difference. Uh, it will be an anyway. So sigma an then can be represented by, just replace an by this value, an plus an minus an, or we can write it sigma an plus absolute value of an minus sigma absolute value of an. Now this series is convergent because this is given. Now this series is convergent because we just proved it. So sum of two convergents or difference of two convergent series is also convergent. Okay, so this means that sigma an is also convergent. Okay, let's apply this theorem in order to prove the convergence of a series. So we have this series sigma minus 1 to the power n plus 1 over 1 over n square. So this series can be represented term-wise like this, and we have a series of absolute values is given by 1 over n square, which is this series, and we know that this is convergent. We have already proved this, we are not going to prove it again. So since the series of absolute values is convergent, so this series converges absolutely. Okay, so this series converges absolutely because the series of absolute values is convergent. And since this converges absolutely, and this actually implies that original series converges. Okay, next, this is another example. Sine n over n square, where n varies from 1 to infinity. Now, sine lies, you know that sine n lies between 1 and minus 1. It can have negative values and it can have positive values as well from 1 to infinity. So series can be written in this form. Apparently you can see that this series has all positive values, but this is not the truth uh, because sine lies between minus 1 and 1. So we can have negative values as well. So we'll check the convergence of absolute series. So corresponding absolute series of absolute values is given by this series, which is equal to this, right? And now we can conclude one thing: sine n absolute value over n square is less than 1. We know that 1 over n square, because sine n, we know that sine n lies between minus n and minus 1 and 1. So sine n absolute value is less or equal to 1. Okay, so sine n over n square absolute value is less or equal to 1 over n square, and we know that this series is convergent. Sigma 1 over n square is convergent. We have already proved it. Okay, converges. Now if this series converges, we can say by comparison test that this series of absolute values also converges. And if this series of absolute values converges, then this series converges absolutely. And since this series converges absolutely, this means the series converges. Next, ratio test. So actually the name indicates that we are going to analyze or examine the ratio of something. So let's see what type of ratio we are going to examine in this test. So the ratio test measures the rate of growth or decline of a series by examining the ratio of two consecutive terms, an plus 1 divided by an, ratio of an plus 1 and an. So for a geometric series sigma a r n, if we take the ratio of two terms, we are going to have a r n plus 1 divided by a r n. This must be n, there is a typo. So what we are going to have after the cancellation, we are going to have r. So this ratio is equal to r. And the series converges if and only if ratio is less than 1, if r is less than 1, right? That is its absolute value of the series. The ratio test is powerful rule extending result. So we are going to extend this idea. In geometric series, we can see that the ratio is less than, if the absolute value of ratio is less than 1, then the series is convergent. So let's see how can we extend this idea for any general series. So this theorem actually gives us the rule to test the convergence of given series by taking ratios. So this is theorem number 13 of the book. Okay, if we have a series sigma an, any series, be any series, suppose that the limit of the ratio an plus 1 divided by an as n approaches to infinity is equal to rho. Of course, whenever we are going to take the limit, there must be some value. It can be a finite definite value, it can be an infinite value. So let's see what is in store for different values of rho we have. So the series converges absolutely if rho is less than 1. Okay, series converges absolutely. So you have to keep this in mind. Series converges absolutely if rho is less than 1. Series diverges if rho is greater than 1 or rho is infinite. Rho is greater than 1 or rho approaches to infinity. Right? And the test fails or test is inconclusive. We cannot conclude anything from the from this test if rho is equal to 1. And we will see this part with the help of example. Okay, let's consider the first case. If rho is less than 1. If rho is less than 1, then we assume that r is any number between rho and 1. Okay, we have 1, and since this is a series of absolute values, so it cannot be negative. So this is 0, this is 1, rho lies somewhere here, for example, and we are going to choose r between rho and 1, that is somewhere here, if r lies somewhere here. That is, r is greater than rho but less than 1. between rho and 1. So the number epsilon is r minus rho. R is greater than rho, so it must be greater than 0. So if we take the difference of r and rho and name it as epsilon, then this must be greater than 0. Now since an over an plus 1 over an absolute value approaches to rho according to this, because limiting value is rho, so this approaches to rho, then this must lie within epsilon of rho. That is, it must lie between the epsilon of rho, because it is very close to rho. So we can say that this is epsilon times rho. When n is large enough, say for n greater or equal to n, in particular, an plus 1 divided by an absolute value is less than rho plus epsilon, okay, which is equal to r. We have already seen that, which is equal to r, where n is greater or equal to n. So this is going to be less than rho plus epsilon. Now, from this we can conclude that for some n greater or equal to n, for this we can conclude that an plus 1, that is n greater or equal to n. So this means that if n is equal to n, this will become an plus 1 over an is less than r, right? So this gives us this inequality, right? That is an plus 1 is less than a ran. Similarly, if we have n is equal to n plus 1, this uppercase n plus 1, then what is the value? We have n, replace n by n plus 1. So we have n plus 2 over n plus n, replace n by n plus 1. So in denominator we are going to have an plus 1, and this is less than r, right? Now this implies an plus 2 is less than r an plus 1, but an plus 1 is less than ran, so this is less than r square an. So we have this inequality. Okay. Similarly, we can derive all these inequalities for an plus 3 and so on. Ultimately, we have an plus m is less than r to the power m an. So therefore, the series sigma am is equal to, where m varies from n to infinity, m varies from n to infinity. So we actually deleted or ignored the first n minus 1 terms of this series, and this is the series of remaining terms, and it can be written as sigma m varies from 0 to infinity, and this is the process of reindexing we learned in the section 10.1. This series can also be written in this form by reindexing. So m varies from 0 to infinity. You can see that we have changed the subscript. M is replaced by n plus n. Now when m is 0, we have an. In this case, when m is n, we have an first term, right? So this is how we can write this series in this form. Now, this is less or equal to, using this inequality, this is less or equal to an r to the power n, because an plus m absolute value is less than this. And since an is independent of m, we can factor it out. So an absolute value, sigma m varies from 0 to infinity r. So we are left with this series times absolute value an. Now this series is actually a geometric series, and what we have assumed that r is less than 1. So r is less than 1, right? And this is a geometric series, so this is convergent. right? So this is convergent series. Now this shows that this series, this one, is also convergent by direct comparison test. This series is convergent and this is greater than this series. Every term of this series is greater than this series. So this series is also convergent. Now this by adding the finite number of terms, we can conclude that sigma a n converges, right? We just have to add n minus 1 terms to make it, rather n terms to make it convergence 1 to infinity or 0 to infinity, because in this case we are not given the starting point, so we can assume that this is starting point is 1. If no starting point is given, we can assume that starting point is 1. So this shows that this series converges, and this series is convergent means this series is absolutely convergent, and if this series is absolutely convergent, then this actual series converges. So this is all about part 1. When rho is less than 1, we see that this series is convergent. Now let's discuss the other possibilities, that is rho greater than 1 or infinite and rho is equal to 1. So if rho is greater than 1 or rho approaches to infinity, then what happens? Then this ratio is greater than 1. And if this ratio is greater than 1, then we can write this am, that is, if this ratio is greater than 1, in fact, this means an plus 1 is greater than an for some n greater or equal to m, right? So this leads us to this relation. Okay, so an plus 1 is greater than an plus 2 is greater than an plus 1, and so on. And the terms of the series do not approach to 0, so they are increasing actually indefinitely. So this concludes that this series is divergent. So if rho lies between 1 and infinite, that is if rho approaches to infinity or rho is greater than 1, then the series is divergent. Now what if rho is equal to 1? Now we will show that the case when rho is equal to 1, the test actually doesn't conclude anything, because the series can be convergent and the series can be divergent as well. So we have these two series. So in both the series, we are going to take the ratio. For the first series, if we have an plus 1 over an, we are actually going to have 1 over n plus 1 divided by 1 over n, that is n over n plus 1, or it can be written as 1 over 1 plus 1 over n. Now letting n approaches to infinity, this will approach to 1 as n approaches to infinity. So, and this series is divergent, we know that. Now what is the case for this series? So in this case, we are going to have 1 over n plus 1 square, 1 over n square, and this also approaches to 1, but this series is convergent. So this ratio approaches to 1, series is divergent. This ratio approaches to 1, series is convergent. So we cannot conclude anything whenever we have rho is equal to 1 for this ratio. Okay, there is a note which needs to be remembered. So the ratio test is often effective when the term of the series contain factorials of expressions involving n or expressions raised to power involving n. That is the terms involving n factorial or the expression raised to a power involving n. For example, investigate the convergence of the series. In this case, you can see we have the terms raised to the power involving n. So we have a series 2n plus 5 divided by 3n, and varies from 0 to infinity. And from ratio test, we have the ratio an plus 1 over an is equal to 2 by 3 as n approaches to infinity. So the limiting value of this ratio as n approaches to infinity is 2 by 3. Now 2 by 3 is less than 1. So what does this mean? This means that this series is convergent. Now this does not mean the sum of the series is 2 by 3. In this case, this ratio approaches to 2 by 3 as n approaches to infinity. So in order to find the sum, we have to do some manipulations, and these manipulations are done in this way. So sigma 2n plus 5 divided by 3n can be written as, just split it into two series. So 2 by 3 to the power n plus 5 over 3 to the power n, and both of these are geometric series with the common ratio less than 1, and both are convergent, and we can find the sum. First term divided by 1 minus common ratio plus first term divided by 1 minus common ratio, and we have 21, right? So this is the sum of the series. So this series converges to this value. Okay. So this test actually, like all other tests, just determine the convergence of divergence. If the series is determined to be convergent, we cannot we cannot actually evaluate the value of the series by the test. For this, we have to do some other manipulations. So investigate the convergence of the following series. We have the series involving factorial and factorial type terms. So, or the factorials of the terms involving n, like 2n factorial divided by n factorial, n factorial. So in this case, again, we are going to take the ratio test. So in this case, an plus 1 over an absolute value approaches to 4 as n approaches to infinity, and this is greater than 1. So ratio test tells us this series is divergent. Again, we have a series with the terms involving powers raised to the power of terms involving n. Similarly, the factorials of the terms involving n, and we are again going to check with the help of ratio test. So ratio test actually gives us the ratio limiting value of the ratio equal to 1. So this approaches to 1 as n approaches to infinity. So in this case, uh, we don't have any conclusion. We cannot say series is convergent. We cannot say series is divergent. So this test leaves us without any conclusion. So how to decide? We cannot decide from the ratio test. However, when we notice that an plus 1 over an is equal to 2 times n plus 1 over 2n plus 1, we can conclude that an plus 1 is always greater than an, right? Because this is 2 times n plus 1 and this is 2n plus 1. So 2 times n plus 1 is greater than 2n plus 1 is always greater than. So this is always greater than 1. Therefore, all the terms are greater than or equal to a1 is equal to 2. So first term of the series is 2, and after that every term is increasing. So every term is greater than or equal to 2. And the nth term does not approach to 0 as n approaches to infinity. Since this is an increasing series, and nth term does not approach to series 0, so this series diverges. So nth term approaches to 0 and the series is decreasing, then we already know that the series will be convergent. That is called nth term test. But if every term is increasing, so or the series is increasing, series, and nth term does not approach to 0 as n approaches to infinity, then series diverges. Okay, next test. This is called root test. So some root is going to be involved in this test, as name suggests. So the convergence test for we have so far sigma an work best when the formula for an is relatively simple. So all the tests done so far actually used for simpler series. Now, what if the series looks like this? That is, an is n over 2 raised to power n when n is odd, and 1 over 2 to the power n when n is even. So, investigate the convergence, we write out the several terms of the series, and this is the term-wise representation of the series, and we can write it as, so there is no actually uh, pattern in the series in general. We just have this pattern. So clearly this is not a geometric series, of course. So the nth term approaches to 0 as n approaches to infinity, but since the terms are different when n is odd and n is even, so we cannot say that this is convergent, but we can say that we even cannot say that series is divergent. So again, there is no conclusion. So the integral test doesn't work, doesn't look promising again. So the ratio test produces this result. Now, if n is odd, it gives us 1 over 2n. When n is even, it gives us n plus 1 over 2. So as n approaches to infinity, this will give us 0 and this will give us infinity. So limit does not exist. So we cannot conclude even from ratio test. So what to do? So let's establish another test, which is called the root test. And this is theorem number 14 in the book. So sigma n be any series as always. So suppose that limit of nth root of an is equal to rho as n approaches to infinity. Now again, rho can be any constant, rho can be less than, now since we are taking the root of absolute value, so it cannot be negative. So either rho is greater than 0, greater than 1, actually less than 1, greater than 1, or infinite or equal to 1. All these possibilities we have already discussed in the ratio test. So we are going to discuss or analyze every possibility in this case as well. So this theorem states that if this rho is less than 1, the series converges absolutely, and if the series converges absolutely, then this series converges. And series diverges if rho is greater than 1 or rho is infinite. Okay, so the test is inconclusive as the ratio test was inconclusive if rho is equal to 1. So let's start with the first case, that is rho is less than 1. Again, we are going to choose the epsilon so small such that rho plus epsilon is less than 1, and since this is given, square root nth root of absolute value of a n approaches to rho, so the terms nth root of absolute value of a n eventually get to within epsilon of p. So there exists an index m, the same argument, such that this is less than rho plus epsilon where n is greater or equal to m, and we can conclude that this absolute value of a n is less than rho plus epsilon to the power n, just raised to the power n both the sides of the inequality. So we have this result. Now the series consisting of these terms, that is rho plus epsilon n, is actually rho plus epsilon to the power n is actually geometric series with rho plus epsilon, which is common ratio, less than 1. So this means this series is convergent. Okay. Now if this series is convergent, then this absolute series is also convergent, where n varies from m to infinity, because this condition was imposed for n greater or equal to m. So if this converges, then we can add finite number of terms in order to make this series convergent. And if this series is convergent, we can this is actually absolute series of absolute values of this series. So this series is absolutely convergent. Now if this series is absolutely convergent, means this is convergent. So if rho is less than 1 in this case, we can conclude that this series is convergent. Now again, if rho is greater than 1 or approaches to infinity, so we are going to have all the indices beyond some integer m. We have this result, that is, this is greater than 1, and this implies an is greater than 1 for n greater than 1 m. So the terms of the series do not converge to 0. The series diverges by the nth term test. And when rho is equal to 1, again we can use the example of sigma 1 over n and sigma 1 over n square series. Uh, the root of absolute value approaches to 1 as n approaches to infinity in both the cases, but this series is divergent and this series is convergent. So we cannot conclude anything when rho is equal to 1. So here are a few examples. So which of the following series converges and which diverges? And we are going to use the root test. So first case we have, let's try and then we'll reveal the result. We have an in the first case. I'm going to try part 1, part A. So an is equal to n square over 2 to the power n, right? So an absolute value is going to be n square over 2 to the power n, and as n approaches to infinity, now we have to take the root. So what is going to be the nth root of this? So this is going to be divided by 2, right? So as n approaches to infinity, we are going to have 1 over 2. Which is less than 1. So this means the series is convergent. For the next series, similar argument, that is, we are going to have the nth root of absolute value of the nth term. So in this case, we have this result, this, and we have 2 which is greater than 1. And since rho is greater than 1, so this concludes that this series is divergent. Now in the last series, we have the an 1 over n 1 plus 1. So nth root will become 1 over n plus 1. So as n approaches to infinity, this approaches to 0, which is less than 1. So this is convergent. Okay, next, consider again the series n over 2 to the power n when n is odd, 1 over 2n when n is even. So we have to check whether this series is convergent or divergent. So we are going to apply the root test. For root test, we have this, taking root of absolute value of these terms. We have square root nth root of n when n over 2 when n is odd, 1 over 2 when n is even. Okay, so what does this mean? That's nth root of this lies between this and this. So since nth root of n approaches to infinity, so what we are going to do, well, pardon me, this is not infinite, this is 1, again a typo. So nth root of n approaches to 1. You can see section 10.1 theorem 5. So if this approaches to 1, so from this inequality, we have 1 over 2 is less or equal to nth root of absolute value of an, which is less or equal to 1 over 2, because this its limiting value is 1. So this is, so what does this mean? Limit of this nth root of absolute value of n is equal to 1 over 2 by the sandwich theorem. And since this 1 over 2 is less than 1, so this means this series is absolutely convergent, and if this series is absolutely convergent, then this series is convergent. So that's all for today.